I'm Bridget Gorney, and I'm going to be walking you through the circuits I designed and tested for Lab 1 of EEE 120. This lab covers several different types of adders, including a 1-bit half adder, a 4-bit incrementer, a 1-bit full adder, and a 4-bit full adder. Let's dive into how each one of these circuits work. So, first and foremost, we have a half adder, which is the most fundamental circuit for binary addition. It takes two binary inputs, which we'll label A and B, and two output values, a sum, and a carry. The sum is calculated using an XOR gate, meaning the sum is 1 when only one of the inputs is 1, and it'll output 0 when both inputs are the same. So when both inputs are going to be 1 or both inputs are 0. The carry, on the other hand, is produced using an AND gate, meaning it only becomes 1 when both inputs are 1. This setup basically mimics how binary addition works. For example, in binary, 1 plus 1 equals 1, 0, which consists of a sum of 0 and a carry of 1. The carryout from the half adder will be much more useful when we move on to more complex adders where multiple bits are involved. Let me pull up my waveform for you. I have all my commands here for this today. All right, so the waveform shows how the half adder behaves when different combinations of inputs are applied. You can see that the sum and the carry outputs accurately reflect the binary addition of A and B. All right, moving on. All right, moving on, we are going to be having our 4-bit incrementer. So the 4-bit incrementer is used to add 1 to a 4-bit binary number. This means that each time the circuit is activated, the input value increases by 1. The way this works is by feeding the least significant bit, or the LSB, of the input into the half adder, which increments it by 1. If the LSB is 1, the carry from this addition generates to the next bit, and so on, in what's called a ripple carry process. This is why the circuit is called an incrementer. It is specifically designed to add 1 to a single unit to the input. The ripple carry process continues until all the bits have been processed, basically ensuring that the entire number is incremented correctly. Pull up our waveform again for this one. All right, so as you can see in the waveform, the circuit properly adds 1 to the 4-bit input, incrementing the number on every cycle, demonstrating the functionality of the ripple carry mechanism. All right, now let's move on to our 1-bit full adder. All right, so a 1-bit full adder basically extends the idea of a half adder by introducing an additional input called the carry in, which comes from the addition of the previous bit in a multi-bit system. The full adder has 3 inputs, which are going to be A, B, and carry in, or as we have abbreviated here, CN, or SIN. And then the carry out, we're going to have our 2 inputs, which are going to be our outputs are going to be our carry out and our sum. I can move my face here. Here we go. All right. So the sum is calculated using 2 XOR gates, which take into account A and B and the carry in. The XOR operation allows the sum to properly handle the cases where either 1 or 2 of the inputs are 1, but not all 3. The carryout is calculated using a combination of AND and OR gates to handle cases where the carry-in should generate to the next higher bit position. This allows the full adder to handle binary addition in a chain-like fashion, basically, where multiple bits are added together and the carryout from one adder becomes the carry-in for the next adder, ensuring that the addition generates correctly. So I pull up our waveform for this one. All right, so in this waveform, we can observe how the full adder works for various different inputs and combinations, accurately computing both the sum and the carryout, especially when the carry is introduced from a previous operation. All right. last but certainly not least, we have our 4-bit full adder. So the 4-bit full adder is essentially 4 1-bit full adders connected together. It takes two 4-bit binary numbers and adds them together along with a carry in if one is present. Each bit of the two numbers is added in parallel, starting from the least significant bit, or the LSB, and the carry out from each bit addition is fed into the carry in of the next higher bit position. This also creates a ripple carry effect that generates through the entire 4-bit number. The circuit is capable of handling not just basic addition, but also overflow conditions. For example, I tested a bunch of different combinations when trying this. So, for example, when the sum of two 4-bit numbers exceeds the maximum value of a 4-bit number, it can represent, so 15 in decimal or 1111. And binary, the carryout will signal an overflow. All right. Last but not least, I'll show you the waveform for this one. All right, so in the waveform, you can see how the 4-bit full adder handles different combinations of input. So when testing this, I included a bunch of different cases, including cases with and without carry-ins, and I also tested for overflow conditions as seen when adding maximum numbers like 1111 plus 1111, which produces a sum that exceeds the 4-bit limit and sets the carry out to 1. So, in conclusion, these circuits demonstrate the fundamental operations required for binary addition. The half adder and the full adder handle single bit additions, while the 4-bit versions scale this process up to handle larger numbers, all while making sure that proper carry generates between bits. Together, they form the basis for much more complex circuits in digital systems. Thank you so much. Once again, I'm Bridget Gorney. This was my Lab 1 for EEE 120, and thank you for watching.